Hey everyone, today I'm competing in Codeforces around 7:30. Unfortunately, I'm off to a bit of a late start, but we will see how we can do anyway. Hold on, why did I get 6 for... Yeah, why do I get 6 for this third to last case? Oh, I see. There we go. Alright, so basically... Okay, I think I see how to do this. "11 samples. Oh. Okay. Making pretty good time, which is good because I started about 2 minutes late, and that's really harmful when you're in such a fast contest. Actually, let's do it like this. Oh, whoops, multitest. 2, 0, 5, 2, 0, 5, 6, yep, -1, yep. Okay, I'm gonna assume this fourth one is fine. Yeah, the fourth one is okay. Alright, this is good. I think. Yep, awesome. Okay, nice problem. Okay, this is a key problem. Okay, so does this work? We'll see. Not sure if it's this simple. 37. Oh, yeah, it's this simple. Damn, should have done that before. C. That's a nice problem though, I like that. Yep, accepted. Nice. I guess this could just be an int, doesn't really matter, but not return. Continue. True. Yeah. There is by the way an O of n solution to this, I'm pretty sure, but I'm not gonna bother since Dijkstra is easy to implement. Actually, no, I don't know if there's an O-then solution. Either way, though, I think this is the easiest to implement. Okay, now we just print the answer. Oh, I called it. I was trying to decide whether I called it T or temp, and I guess I forgot what I did. Alright, that's fine. Yeesh, okay. Oh, wait. Oh, I'm dumb. Oops. Okay. There we go. Let's see. Alright, this is not correct. Why are we getting like a bunch of... We should be getting numbers that are significantly larger. Oh, I see. I'm reading the input in the wrong order. That looks much better. I feel like brute force is probably sufficient here. Wait, is it? No, it's not. Look at G real quick. Okay, this I know how to do, but it's going to be a little bit annoying. So let's see if this can be done cleanly. Okay, I think I see how to do this. Sieve. Oh, I guess first let me do this. gonna be fast enough? I feel like there might be some constant factor stuff going on here. Wait, no, this is fine. Yeah, this is okay. Actually, I guess I can optimize this a little by doing this. Actually, I think that's more trouble than it's worth. I don't think it's going to TLE, and there'd be some annoying stuff to do with the multitasking here. All right. There's no reason this should be an LL. What? Oh, I used Kurt twice. That's not good. Let's rename this one. How are we getting 42 here? Why is one in? Oh, I'm stupid. Alright, so this one should be 3. Oh, is it just... Yeah, because you can only go to the right, not to the left. Why is this not activating? Oh. Shoot, okay. That was stupid. One. Oh, yeah, I guess I better comment on my debugs. Okay, well, that should not have taken me as long as it did to fix, but that's fine. Got my variables a little confused there. TLE. Okay, that's not good. So why is CF running so slowly? Okay, guess I better go to M2. I mean, I can cut, let's see, so I can cut out a, I can cut out like a log factor, but I don't really, I actually don't really see why that would be necessary. I mean, I guess I might as well. Except how do I do that in a way that's not gonna... Oh, you know what? I'm an idiot. I'm checking all the primes rather than just the small primes. Yep, that would do it. Okay. And then for this next problem, I actually am going to need to pull out my SCC template because I think this is going to be I think this is going to be a easier problem to solve on the condensation graph. So Okay, so let's just start by reading in the graph. I hope my SCC algorithm handles self loops correctly. Oh, and I guess that's another thing I'm gonna need to edit is, okay, yeah, so let's take this one step at a time. So, I n a cube I equals a. Okay. And now let's build the condensation graph. Oh, and I need to clear this mult. Is there anything else that I need to clear? Nah, that seems good. Okay. So now here's what we do. I have very little confidence in this, but well, I have confidence in the idea. I don't have confidence in my ability to get the implementation right, or to have gotten the implementation right. So there may be some debugging involved. Yeah, there's already an infinite loop. That's fun. Okay, so I guess the first step is to figure out where it is. Oh, I know where it is. Now let's hope that's the only one. 1, 0. Okay, so let's see, how is it that some of these unvisible vertices that are, oh wait, no, they are visible. It's just that yeah, it's just that they're visible in infinitely many ways, not just, oh, I get it. Yep, there we go. 1, no, 1 zeros, 1, 1, 2, 1. Let's submit this. I guess I should make sure that my F passed this time, because I actually, yeah, it did. Perfect. Alright, WA. That's unfortunate, because this is going to be really annoying to test. Which debug that is. So let's see, I think I'm handling multi-test correctly. Let me make sure about that. I should make sure that my SCC's implementation handles self loops correctly. Because if not, I can just erase them. Okay, yeah, they do handle it correctly. That's good. Okay. Oh, you know what? It's because I gotta process these in a topological order. And since it's a DAG, that should be fine. Oh wait, but I guess the one thing is, what if we have vertices that can't be reached? Okay, so I guess I'd actually better do it like this. Yeah, so then the answer for the first component yeah, okay, I think this is valid. Let's test it. Yep, okay. That makes sense. Hopefully it's not still WA, but I'm not certain about that. Okay, that fixes it. All right, perfect. Yeah, so that's the contest. Certain things there took me a little longer than I would have liked. Had to do some debugging on F that was a little annoying. And then also, obviously, the 2 penalty submissions in a div3 is not ideal. And then having to start late cost me, like, I don't know, probably probably at least 7 penalty, maybe like 7 to 12 or so. But overall, pretty good contest. Can't be too disappointed with how I did. Let's check the standings. Oh, nice. I am in first so far. Can hit on a node pass me? 72 plus 36. Yes, so these 2 people have several minutes to pass me. So it looks like it would have been pretty clean if not for my penalty submissions. As is, they've got some time to finish G. Hopefully it's going to take them a little longer than it took me. I was definitely advantaged here by having a nice SCC implementation ready. So, you know, obviously if they don't have those prepared, then I'll be in a nice position. But otherwise, you know, second or third would not be bad. And I think, like, at this point, any of these guys can't pass me. So, oh yeah, it looks like this guy is about to win. I think that must be an alt, because there's no way that a green is someone who's green is going to get first place overall. Yep. Okay. So that's unfortunate because it means that I would have gotten first if not for either of these penalty submissions. But still a pretty good performance overall. Be curious to see if I end up getting passed by hit on node. Okay, anyway, let's go ahead and talk through some of the problems. Now let's see, I'm going to test something real quick. Let's see, can I do, is this something I can do? Okay, actually no, I'll test things in the next video. So, all right, let's pull up the problem set. And then I'll get my notepad ready. I've received a request to increase the font size during my explanations, so I will go ahead and do that. Stick to 14 point for now, and we can see what people think of that later. Okay, so problem A. So we have an infinite two-dimensional grid with 3 cells, and we have to find the length of the shortest path from A to B, given that we can move between any 2 cells sharing a side, but we can't visit the cell F. All right, so here, let's think about how this is typically going to work. So what this is typically going to look like is, let's say we have A up here, and then B down here. Now, typically what we could do is we could just go like right, or we could just go like right, down, down, B, and that would get us there efficiently. But then let's say F is in the middle. And if that's the case, then we can take a detour and we can go down, 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 right, right, right. And so we can avoid the obstacle altogether, while taking no more moves. And so, and in general, the idea here is the shortest possible, or that essentially there's going to be a number of horizontal moves we have to take in order to get from A to B, and keep in mind that in each horizontal step we can increase or decrease x by 1, and we need to get xa from xa to xb. So we're going to need at least the absolute value of xa minus xb horizontal steps, and likewise we're going to need at least the absolute value of ya minus yb vertical steps. And so in total, the answer is at least the absolute value of xa minus xb plus the absolute value of ya minus yb. And in most cases, this is actually going to be achievable. And the way we do that is by going horizontal and then vertical. Or if that path would intersect with F, then we're going to need to go then we can go vertical and then horizontal. And none of the cells on this path intersect with any of the cells on this horizontal and then vertical path. And so that tells us that if F is on this path here, then it's not going to be on this path here. And so that means that as long as we've got both of these 2 possible paths, then this thing right here is going to be the answer. And so that implies that in most cases we have our answer figured out. But then the question remains: is this always achievable? Are there going to be any cases where this doesn't work? And the answer is yes. And so the idea here is this approach of take horizontal steps, then vertical steps, but if this would encounter f, take vertical steps, then horizontal steps. So this works if whenever there are both horizontal and vertical steps to be taken. But what happens if our path is all horizontal or all vertical? So for example, let's say that our diagram looks like this, and we've got f in the middle right here. In this case, there's no path that we can take that goes straight from A to B, because without thinking about f, the only possible path would be just to go down, 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 down. But that path would encounter f, so we can't use it. And so what that means is we're going to need to go around f. And the most efficient way to do so would be to go down, down, and then go right, and then down, down, and then go left, and then go down again. So it's basically a two-step detour, because we're adding two horizontal moves that we wouldn't need if not for f blocking our way. And so in general, the way this works is if A, F, and B are on the same horizontal line or the same vertical line with F between A and B, a detour is necessary and will add 2 steps to our answer. And so now I'll talk about how I implement my solution, and I apologize because my variable names are not particularly consistent with what are used in the problem. I used A for X, A, B for Y, A, C for XB, D for Y, or for YB, E for XF, and F for YF. But I'll try and explain this in a way that's consistent with the problem statement. So first I define this variable ans, and this is just the default answer I get up here. But then I have to deal with the separate cases. So the first case here, this if statement checks if all 3 x coordinates are the same. And if the 3 x coordinates are the same, that corresponds to the 3 points being on the same vertical line. And so the next thing I need to check is whether f is located between A and B on this vertical line. And the way I do this is by adding all of the y coordinates to a vector, sorting it, and checking if the middle y coordinate corresponds to f. And if that's the case, then we need to take a detour, and so I increment the answer by 2. The second block does exactly the same thing for if the y coordinates are equal, so if A, F, and B are on a horizontal line together. And so I create this vals vector that stores the x coordinates of the 3 points, and I check if the middle value in there is equal to the x coordinate of f. And if so, then we need a detour. I add 2 to the answer. And then I just print the answer, and we are done. Okay, so that's problem A. And then I'm going to check real quick to see if I have been passed. Yep, I have. So unfortunate that I got those penalties because would have taken first without it, but that does happen. That is kind of just a risky take with div 3s. And my error on G, I kind of get why I made it because it was a little tricky, but F I'm a little disappointed in myself for getting that TLE because that was a very dumb mistake. But oh well, moving on, let's look at problem B. So a string S of length n is called alphabetical if it can be obtained by starting with an empty string and then performing n steps, where at the ith step we take the ith letter and we add it either to the left or to the right. And so then we have a given string and we want to determine whether it's alphabetical. Okay, so there are a couple of ways to do this. One that would be pretty intuitive would be to say, okay, like let's simulate the process in reverse order. And so what we can do here is we can say like, okay, what's the last letter that would be placed? Is it on the left or the right of the string? And if so, let's remove it and continue. So for example, for this sample input BAC, so we have n is equal to 3, so the last letter to be placed would be C. We can see it's placed at the end of the string, so that's okay, we can remove it. And then before that step, we must have had the string BA. B is on the left end of that string, so we can remove it. And then we get to A. A is on both the left and the right of the string, so we can remove that. And then we're down to the empty string. And at that point, we can see that all of these steps could reasonably have been processed, so we're good to go. Whereas in contrast with, let's take a look at this sample input, ACB, we'll see is neither on the left nor the right of the string, so it could not possibly be the last step that was made. And so that's, and so that case would not, and so this case is a no because the operation, the add C, could not have been done last. So that's one way to do it. I think it's relatively easy to conceptualize. It's not the way that I did it. So the way I did it uses the fact that we're going to start with A at the center, and then the strings are going, and then the letters are going to get larger and larger as we sort of go outwards from A. So like, for example, we might have A, B, E, or B, D, F, H on one side, and then A on the other side, C, E, G. And we can see that as we get further and further away from A, the letters grow larger. So like when we read it to the left, the part going after A is increasing, and we read it to the right, the part going after A is increasing. Like on the left we have A, C, E, G, that's increasing. And on the right we have A, B, D, F, H, which is also increasing. And so that's what my solution makes use of. And so the idea then is that if I comes before the position of A, then S of I should be less than S of I minus 1. And that's because until we reach A, we're sort of going to be decreasing the letter on and on until we reach A. So we go, so E is less than G, so that's fine. C is less than E, so that's fine. A is less than C, so that's fine. If I comes after the position of A, then S of I is greater than S of I plus 1. And this is because, and so, for example, here we have A, B is greater than A, D is greater than B, F is greater than D, H is greater than F. And intuitively, the reason that this is true is that this represents basically that we're going to add, or the way we can add characters to the left of the string. And whenever we add a character to the left of the string, it's going to be larger than all the characters we've seen so far. And so that means it's definitely going to be larger than the character immediately to the right. And that's why S of I minus 1 is greater than S of I. And here, this represents how when we're adding characters to the right of the string, they're going to be larger than the character immediately to their left. And if a character comes after the position of A, then it was added to the right of the string, so it must be greater than the character to its left. And if it's to the left of A, then we must have added it to the left at some point, so it's going to be greater than the character to its right. And so my solution essentially checks that these properties hold, as well as ensuring that S is a permutation of the first n letters. Because obviously if some letter outside the first n letters appears, or if some letter appears multiple times, then that's not going to work. So the way I implement this is essentially using a chew point. Oh wait, sorry, I opened my C code. Okay, the way I implement this is I iterate over the letters in the string, and then first of all, this conditional checks if the index of the letter is at least n. A helpful trick, if you aren't familiar with it, is you can get the numerical index of a letter by subtracting the character A from it, and that's going to give you basically a zero indexed representation of the character. That means that means A has index 0, B has index 1, and so on. So that means that the characters that we're looking at have indices 0 through n minus 1. And so if S of I has index at least n, then it can't be added during this process, and we print no. This statement, it's a little terse, but it essentially checks these two conditions here. So found of 0 represents whether A has been found yet. And so if A has been, and so I say, okay, if A has been found yet, or has been found already, and this condition fails to hold, so S of I is actually less than S of I minus 1. Oh, sorry, this should be a minus, not a plus. Then I print no, or alternatively, if A has not been found yet, and S of I is greater than S of I minus 1, this condition is violated, so we print no. And then the last thing I do is I enforce the rule that S has to be a permutation. And the way I do that is by saying, okay, if we've already found this letter, then we print no, and otherwise we say, okay, yes, we found it. So yeah, there's a couple of different ways you could implement this problem. That other approach I mentioned to sort of simulate the process backwards, you could do using a chew pointer sort of approach. This is just sort of what I thought at first within the context, or within the contest. I'm not really sure why, because I think the other argument is maybe a little more intuitive, but yeah, either way, I think, I mean, they both work, obviously. So let's move on to problem C. Actually, I'm not going to pull up my code yet. Okay, so we have two people, one of them working, and one of them has performed n changes to a file, one of them has performed m changes to a file. And essentially, each action consists of either editing a given line or adding a new line. And of course, you can't edit a line that doesn't exist. And the goal is to figure out a way that this could have all happened, such that the order of the operations is maintained. So, for example, Monocarp's first operation was performed before a second operation, and such that nobody edits a line that cannot be or that has not been added to the document yet. All right, so there's a key observation here, and the observation is that essentially no operation is going to limit our options later on. So that is, if we so that more formally, if there's an action that we can perform right now, and then we perform another action first, we're still going to be able to perform that first action later. So, or I can write that out here. So suppose operation X is valid. Then if we perform operation Y instead, X will still be a valid operation. And so what this means is that, for example, if we, in other words, so at any given point, the operations we can perform are we can add a line or we can edit a line already in the document. And if we perform another operation first, then the only change that could possibly be made is another line could be added. But either way, we're still going to be able to add another line or to edit edit a line that was already in the document in the first place. And so all of this is basically to say that we don't really need to be strategic about prioritizing the operations or the order or the operations that are like more important in some sense, because what we can do is we can just say, all right, let's just look at the two operations that are next in, or that we can look at Monocarp's next operation and we can look at Polycarp's next operation, and if one of them is something that we can do, then let's just do it immediately. And we don't need to do any sort of particular strategic optimization here, because the order doesn't really matter as long as we never perform an invalid operation. So this problem I implemented using a chew pointers approach, and so I initialize these chew pointers to both be 0. P1 represents a point within Monocarp's array A, and P2 represents a point within Polycarp's array B. And so then K, I just maintain that it as a variable storing the number of lines in the document. And so I first check if P1 is less than N, and the operation is less than or equal to K. Because if the operation is at most K, then either it's going to be 0, in which case it's adding a new line, which is always valid, or it's going to be editing a line from 1 to K, and those lines are already in the document, so that's also valid. And if that's the case, then I set use 1 to true, and that means I'm using the first array, I'm using Monocarp's array. Otherwise, if we can't use the operation from Monocarp's array, then we say, okay, can we use an operation from Polycarp's array? And if so, then we set use 1 to false. But if we can't use an operation from either person's array, then we can't do anything. There are no more operations left. And so in this case, it's impossible. We print -1 and we terminate. And now I just say, okay, if we're using operation 1, then I'm going to add the next operation from Monocarp's array, and then increase P1. And same thing for Polycarp's array if use 1 is false. And then the next thing I do is if the operation we just added is a 0, then that adds a new line, so I increment K. All right, awesome. So let's go over problem D. Yeah, I actually think this was a cute problem, maybe my favorite problem from the set. So a sequence of non-negative integers is called growing if all ones in a sub I are also appear in a sub I plus 1 in their binary representation. And so we're given a sequence x sub 1, x sub 2, x sub n, and we want to find the lexicographically minimal sequence y sub 1, y sub 2, y sub n, such that x sub I and y sub I are co-growing, i.e. the sequence formed by the XORs of the elements of x and y form a growing sequence. Okay, so the first thing to notice here, and this is a general property of every single problem about finding a lexicographically minimal sequence, so this is a very good general fact to know. Any problem where you're trying to construct a lexicographically minimal sequence should be approached greedily. And what I mean by that is, if you're trying to minimize a sequence, what that means is that you care most about minimizing the first element before you can, and even if that means that all the other elements are going to have to be really big. So that means that what we're going to do here is we want to find the smallest possible value for y1, and we're not going to worry about what that does to y2 up to yn. And then based on that decision that we made, we're going to find the minimum possible value for y2 and so on. Okay, so that begs the question of how do we find the minimum possible value for y1, or how do we find the minimum possible value for y2, or so on. So, okay, let's let k be, or so let's say we're processing suppose we're trying to minimize y sub I. So let's let k equal x sub I minus 1 XOR x sub, or y sub I minus 1. I minus 1, sorry, I don't know how to type. And then if I equals 1, then k equals 0. And so the idea is k must be a submask of x sub I XOR y sub I. That is, every bit that's set in k must also be bit set in x sub I XOR y sub I. Okay. And so then the other idea here is that even if a bit is a 0 in k, so I guess first of all, so that means bits that are 1 in k must be 1 in x sub I XOR y sub I. And so that essentially locks in what y sub I has to be if a bit is 1 in k. Because if x sub I is 1 in that position, then y sub I has to be 0 to keep it as a 1. And if x sub I is 0, then y sub I has to be 1 to turn it into a 1. So now what about bits that are 0 in k? Then let's do some casework. Let's say, first, suppose they're 0 in x, or well, actually no. So here's a better way to explain this. So then, we don't care whether they're 0 or 1 in x sub I XOR y sub I. Either way is fine. All we care about is minimizing y sub I. And so what we're going to do is we're going to say let's just set y sub I, set these bits to 0 in y sub I, because that's how we minimize y sub I, by setting bits to 0 rather than 1. And an equivalent way to phrase this that I'll show you in my implementation leads to some really concise code is that x sub I XOR y sub I is going to equal 1 if x sub I is 1, or 0 if x sub I equals 0. And so in total, x sub I XOR y sub I will equal 1 wherever k is 1 or x sub I is 1. And an equivalent way to phrase this is that x sub I XOR y sub I is going to be the bitwise OR of k and x sub I. And moreover, we know that, a good property of x sub I, or of XOR to know, is that is that essentially we can cancel things out by XORing them again, in that y sub I, so if we XOR both sides with x sub I, then they're going to then on the left hand side the two x sub i's cancel out, and so this is equivalent to y sub I is equal to k bar x sub I XOR x sub I. And so this motivates a really nice concise solution that I implement here. So this curve variable is where I store k, and then here I say, okay, the new value of k is equal to k or x sub I, and then y sub I is going to be the new value of k XOR x sub I. And that's all there is to it. So there's a lot of math, but in the end, there are only, other than like the multi-test stuff, I guess, there are only 8 substantive lines of code. So this turns out to be implemented, or this turns out that you can implement it really concisely if you want to do so. But there are also some other ways to, or there are also some longer ways to implement it. Like for example, if you didn't want to rely on these bitwise operations, then you would be able to just like go bit by bit, so like loop for j from 0 to 30 and do something for each bit j. But this is probably the cleanest possible solution. Okay, problem E, air conditioners. All right. So we're given, or so we have a strip of length n, and there are k air conditioners, and the ith air conditioner is at cell a sub I, and we're also given that every air conditioner is in a distinct location. And so the temperature in a cell is calculated by equal to the minimum minimum of the temperature of an air conditioner plus the distance from that cell to an air conditioner. And so then we want to find the temperature of each cell. All right. So it turns out that like something that you might find surprising here is that we can actually model this as a graph problem of sorts, and we can ultimately solve it using Dijkstra's algorithm. And the idea here is if we so let's say that we're looking at this sample case. So initially we have this air conditioner at position 2 with temperature 14. And the idea here is we can move to the left or the right, increasing the distance from this air conditioner by 1, as long as but that's going to increase the temperature by 1. So that means that we can set the temperature, so that means that if we go to the left, we can set the temperature of cell 1 to 15. If we go to the right, we can set the temperature of cell 3 to 15. If we go to the right again, we can set the temperature of cell 4 to 15. And the way we can model this as using a graph is we can initialize the distance to each cell to be its temperature, and then we can also initialize and then we can set up a graph where there's an edge between every two adjacent cells on the strip with distance 1. And let me write all that out. So initialize, so model the problem as a graph where the distance to a vertex represents its temperature. Initially, the temperature of a sub I is going to equal T sub I. That is, for the ith air conditioner, the temperature at its position is equal to its temperature. Then consider a graph. With edges from vertex I to I minus 1 and to I plus 1, where all edges have weight 1. And then we can compute the temperatures by running Dijkstra's algorithm on this graph. And the reason we have to perform or run Dijkstra's algorithm rather than BFS, even though this graph is unweighted, is that the initial distances may be different. And that's not something that BFS handles particularly nicely. There is a way, theoretically, to implement this using BFS, and that would get you an O of n rather than O of n log n running time, but I would not recommend it because it makes the code much messier. So the implementation should be fairly standard to people who have seen Dijkstra's before. So initially I set up this priority queue, and I set up my temp array. And then I initially push every air conditioner into the queue. And then I store this visited array to make sure that I don't visit the same cell twice. So then I start by taking the current vertex out of the queue. If this vertex has been visited, then I skip it, and otherwise I say, okay, now it has been visited. And so here I say, okay, so this represents the edge from x to x minus 1. And I say, okay, if we can decrease the temperature at x minus 1 by setting it to the temperature at x plus 1, then push it into the queue. And same thing here for if the temperature, or for the edge from x to x plus 1. And then that's really all there is to it. In the end, I just output all the temperatures and I'm done. So yeah, I encourage you to take a look at the editorial, which will probably give you a slightly more formal treatment of the reduction from the original problem to the sort of graph structure and the Dijkstra's algorithm. But yeah, I think it's always interesting to see how a problem that doesn't immediately look like something related to graphs can actually be solved using a graph algorithm. Okay, problem F. So we're given an array of positive integers a, and then we have an algorithm where we construct a new array b, where b sub I is equal to the GCD of a sub I and a sub I plus 1 mod n, so the next element to the right in the array. And we want to find the minimum number of steps after which all values a sub I become equal. All right. So let's start making some observations. First of all, let G be the GCD of all the elements, so a sub 0, a sub 1, up to a sub n minus 1. We can observe that no GCD, or that everything is always, that like all elements of A will always be divisible by G. And then what we're going to prove is that all other factors are eventually going to be removed. And so that means that, that means that ultimately the final array will have a sub I equals G for all I. And so now what I'm going to do, just to simplify things, is I'm going to divide all the elements of a sub I by G. And so now the GCD of all a sub I is 1. And that's going to make the problem easier to think about. Okay. The other thing to realize is that we're essentially trying to eradicate also all prime factors from the new array A. And those are sort of happening in sequence, in that like dividing through or getting rid of factors of 2 is separate in the GCD algorithm from getting rid of factors of 3, because the GCD algorithm looks at all prime factors independently. And so what that means is now we want to compute the maximum time it takes for any single prime factor to no longer appear in A. Because in order to get a sub I equals 1 for all A, which is now what we're trying to do since we want to have a sub I equals G and we've divided everything by G, we're going to need to get rid of every prime factor. And so the limiting factor is going to be whichever prime takes longest. Okay. Now, let's say that we have a Boolean array for a given prime factor, storing whether that prime is a factor of each element of A. So, for example, for the second element, or for the, let's say that we're looking at the first sample case, and let's first of all, the GCD, we can see that the GCD of 16 and 5 is 1, so G is going to be 1, so we don't have to divide here. And so then let's say we were looking at the Boolean array for corresponding to the prime 5. Okay, so 16 is not divisible by 5, so that's going to be 0. 24 is not divisible by 5, so that's going to be 0. 10 is divisible by 5, so that's going to be a 1. And 5 is divisible by 5, so that's going to be a 1. And so the idea here is after we perform these GCD operations, then we can see up here that B becomes 8, 2, 5, 1. And we can see then the new array is 0, 0, 1, 0. And in fact, after one more step, this 5 is going to turn into the GCD of 5 and 1, which is 0. And so we get 0, 0, 0, 0. And that's what we want. We want the array to be all zeros because then nothing is divisible by that prime factor. And in general, we can verify that in a given step, all ones that are immediately to the left of a 0 become zeros. The result is that the answer for a given prime is the longest streak of ones, i.e. the longest streak of consecutive elements in A sub I, or in A, that are divisible by that prime. And the idea is that within that sort of streak or that chain, each step is going to turn one of those elements into something that isn't divisible by that prime. But only one at a time, because only one element in a streak is going to be immediately to the left of a 0. And so ultimately, what we want to do is we want to find the longest chain, or we want to find the longest chain corresponding to any prime. Okay, so let's see. Is there anything else I need to say before I get into the code? Let me think about this for a moment. Okay, yeah. Now the problem that we face here is that A sub I is up to 10 to the 6. I don't know how many primes there are up to 10 to the 6, but I would estimate about 50,000-ish. And if we try to construct this Boolean array for all 50,000 elements, well, we have 200,000 elements, and 2 times 10 to the 5th times 50,000 is 10 to the 9th, I believe. Maybe 10 to the 10th, which obviously is way over 10 to the 8th, which is generally the number of operations we can process in a second. So that's not going to work. So we aren't going to be able to explicitly construct the Boolean arrays, and we're going to need to count the chains in a better way. And I'll show you how I do that in my code. I think that's going to be the easiest way to explain it. So the first thing I do is I have my sieve template up here. I think I took this off of CP algorithms or another similar source. And initially, like before I do anything, I compute all the primes up to 1,000. And the idea here is if we're trying to factor an element of A, we can check it for divisibility by all primes less than the square root of its maximum value, so 10 to the 6th. And then if we still have a factor that we haven't gotten through yet, that factor must be prime. And the reason is that if x is up to 1,000,000, x cannot be the product of two numbers that are greater than 1,000. All right, so in my code, the first thing I do is I compute g, and then I divide everything by g. And now I initialize the answer to 0, and we're going to calculate it. So the first step I do, and that covers these 10 lines up here, is I factor the current element in A. And so I initialize this value x to A of p, and then I go through all the primes. And if it's divisible by a prime, the first thing I do is I add it to cur, which stores the list of prime factors of the current number. And then I divide it by A until it's no longer divisible by A. And then if x is greater than 1 at the end, so if there's still factors left over, I add it to the list of primes too. So you might have noticed here, is that I loop up to 2 times n rather than n here. And the reason I do that is because this operation is essentially taking b sub I to be GCD of A sub I and A sub I plus 1 mod n, our operations can sort of wrap around the end of the array to the beginning, i.e. like the last element is also going to be GCD'd by the first. And what that means is that when we're looking for these chains, we could also look at chains that sort of wrap around and go back to the beginning. So like, for example, if we have the sequence 1, 0, 0, 1, we could then the answer would be 2, because we would have a chain that begins at this last element and continues on to this first element. And the way I deal with that in my code is I essentially repeat the sequence A twice. So like this. And then the idea is that any chain that sort of wraps around will include like both the end of the first copy of the array and the start of the second copy, and so that's how we get 2 in here. And so this is a common trick to like sort of repeat the sequence twice when you're given a problem on an array that can potentially wrap around. All right. So afterwards, I iterate through each prime factor, and what I do here is I maintain two maps. And the first map stores the last position in which a given prime has been seen, and CNT stores the length of the current streak of that element. And so I split into 2 cases here. So the first is if this element has been seen before and the last time it was seen was just immediately to the left, then what that means is that we're sort of continuing a streak of seeing this prime. And so that means we increase its streak length by 1. And otherwise, we're not continuing a streak, so its length is 1. And then we reset the last time we've seen this element, and then we set the answer to the maximum of what it currently is, or the length of the current streak, because we're ultimately looking for the maximum streak length overall. And once this loop finishes, we just print the answer. Okay, great. So let's look at problem G. So we're given a directed graph G, which can't contain loops, and we want to determine for each vertex whether in case 0 there are no paths from vertex 1 to that vertex. In case 1, there's exactly 1 path to that vertex. In case 2, there are multiple paths to that vertex, but the number of such paths is finite. And then negative 1, the number of where the number of paths from 1 to that vertex is infinite. Okay, so the key intuition here is, the key observation is that the answer is -1 if and only if there's a cycle between 1 and, or there's like a cycle somewhere between 1 and the vertex in question. And the idea here is if we can go from 1 to a cycle and then to a certain vertex, then we can get an infinite number of paths just by varying the number of times we go through the cycle. So for example, let's show that there are infinite paths in the sample graph from 1 to vertex 6. Well, we could go 1, 4, 5, 6. We could go 1, 4, 5, loop around to 5, then 6. We could go 1, 4, 5, loop to 5 again, 6. 1, 4, 5, loop, 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 6. And so on. Any number of loops, that gives us an infinite number of paths. And so what this motivates here is that it seems like we're going to be very interested in the cycles. And what this motivates is that the strongly connected components of this graph are going to be relevant, because a strongly connected component that either contains a self-loop or contains multiple vertices is going to include a cycle. And likewise, any cycle is going to be within a strongly connected component. That is, like, there's never going to be a cycle that is there's never going to be a cycle that includes 2 vertices in different SCCs. So this motivates looking at strongly connected components. In particular, we're going to examine the condensation graph, which is, and the condensation graph, if you aren't familiar, so I guess first of all, I'll just define both SCCs and a condensation graph. There's a good article about these topics on cpalgorithms.com if you're curious. So I would encourage you to take a look if you haven't seen these concepts before, because I'll just be defining them briefly. A strongly connected component is a set of vertices such that there exists a path from each vertex in the SCC to each other vertex in the SCC. And an important thing to note here is to note that all SCCs with at least 2 vertices contain a cycle. And then the condensation graph, the condensation graph is a graph where each vertex is an SCC, and there's an edge from one vertex to another if there exists an edge from the first SCC to the second SCC in the original graph. And an important fact that you should try proving if you aren't familiar with it already is that the condensation graph is a is a DAG. That is, it's a directed acyclic graph. All right, so there's a well-known algorithm to build the condensation graph. I'm not going to cover that there. If you haven't seen it before, I'd encourage you to look at CP algorithms. I actually have the link pulled up, so here's a link if you're interested in learning more. All right. So we can build. So suffice it to say that we can build the condensation graph. How do we use it to solve the problem? So first of all, we can identify when the answer is 0 pretty easily, right? Like it's a well-known problem to see for which vertices are reachable from a given vertex. What about now? Distinguishing between these other 3 answers is the harder part. And so here's the idea. The first thing we're going to do is for each SCC, store whether it contains a cycle, and an SCC contains a cycle if it includes multiple vertices, as I said above, or if its one vertex has a self loop. So, for example, in this sample graph, the SCC containing only vertex 5, it has a loop, and so it's going to contain a cycle. All right, and so then, suppose an SCC is reachable from vertex 1, then all vertices reachable from that SCC will have answer -1 for the reasons I described when I was first getting started. Suppose an SCC with a cycle, and then all other vertices will not have answer -1. And so this is it's not too hard to prove, I don't think, but it's a little bit more annoying to do so, so I'm going to omit it. The basic idea is that if there isn't a cycle, if there isn't a cycle between vertex 1 and another vertex, then we're working with a directed acyclic graph from vertex 1 to that vertex, and there are a finite number of paths on those we can prove. Okay, let's see. So that lets us figure out which vertices have answer -1. So all that's left is we need to figure out how to distinguish 1 or 2. And so the idea here is so that if a vertex is directly reachable from multiple strongly connected components, it has answer 2. And that's because there's 2 ways we can go through: the first SCC or the second SCC. Alternatively, if a vertex is directly reachable from an SCC with answer 2, then it has answer 2. And so the idea is that we can take the first or the second path to the last SCC, and then we can go to the next SCC. And then otherwise, the vertex has answer 1. And I guess something I should note here is that we can prove that the answer is going to be the same for all vertices within the same SCC. And the proof is actually pretty simple, because if the SCC has a cycle, then its answer is going to be -1, and otherwise it's just going to be 1. It's just going to contain 1 value. And so it makes sense to talk about the answer for an SCC, because in order to restore the answer for the original graph, we can just, for each vertex, print out the answer to it, or the answer for its corresponding SCC. Okay. So that tells us how to distinguish between the four answers. So let me walk through how I translated this into my code. Okay, so the first thing I do is I reset all of my arrays, because this is a multi-test problem, and so we need to reset everything. I read in the graph, and then I compute the SCCs. And in this find SCCs function, the one part of it that isn't templated is these 7 lines right here, where I'm trying to figure out what to do with a new SCC. And what I do is, first of all, I have this vector comp here that stores the SCC in which each vertex is contained. And so I initialize that, and then I also check whether the SCC contains a cycle. And I do that in this isMult vector. In this part, I say, okay, if it contains multiple vertices, then there must be a cycle. And then down here, I say, okay, if there, for any self loop, that any cycle or any SCC containing a self loop must have a cycle. Okay, so the next thing I do is I build the condensation graph. And the way I do that is by iterating over all edges, and if the edge is between two different SCCs, then I add the corresponding edge to the condensation graph. I use a set here so that to guarantee that I'm not going to accidentally add multiple copies of the same edge. All right, and then I create this answer array. And initially I say, okay, the answer for every SCC is 0 because we haven't found it yet, with the exception of the first component, which I'm initializing the answer to be 1. Later on, I'll make sure that the answer to the first connected component, or to the connected component of vertex 1 can't be -1, but for now I'm just setting it to 1. And then what I'm going to do is I'm going to process the SCCs in topological order. And recall that, from what I said earlier, that the condensation graph is a directed acyclic graph, and that means it's guaranteed to have a topological order. And for those of you who aren't familiar, a topological order is an ordering in which each SCC comes after all the SCCs with edges to that SCC. So that is, given a vertex V will come after all vertices U such that there exists an edge from U to V. That's what a topological order is. And the idea here is that once we've processed all of the SCCs leading into a certain SCC, then we know that the answer for that SCC is final, that it's not going to change later, and so it's safe to process it and move on. And the way to construct a topological sort is to store the in degree of each vertex, and then just to add a vertex to the queue only when its in degree is 0. All right, so that's how I build the topological sort. And then what I do is I start by taking a new value, and then if I say, okay, if this SCC contains a cycle and it's reachable from vertex 1, so its answer is not 0, then its answer is -1. Okay. And now I consider all of the SCCs reachable from this SCC, and so obviously if the SCC V is not reachable from 1, then it's not going to make any other SCCs reachable from 1 either. So this inner step I do only if our answer is not 0. Now the first case is if the answer of the next SCC is 0, if there's no way to find it, then I initialize its answer to be equal to the answer for SCC V, because all the paths to A will go through a path to V, and so there will be the same number of paths to A and V. Alternatively, if the answer of V is -1, if there are infinitely many paths, then there are definitely going to be infinitely many paths to there are definitely going to be infinitely many paths to A. And now in this last case, what we know that there are finitely many paths to V, and we know that there's at least one path to A. And so what I say is, if there are finitely many paths to A, then that means there's at least one path to A already, and there's at least one path to A that goes through V that we haven't processed yet. So that means there are multiple paths to A, and that means that the answer for A is 2. And so then I decrement the in degree of A since we processed an edge, and if its in degree is now 0, I add it to the queue. And afterwards, I print the answer for each vertices component. All right, great. So that's a contest. Yeah, so pretty straightforward round. As you can see, 170 people have solved the last problem, so probably quite a few of those are AKs. Let's see how many people have finished the set yet so far. Yeah, so 111 people have finished the set in the first hour, 15 minutes. Obviously, I think there will be quite a few more of them later on. A little unfortunate that I had to get a late start by a minute or so, since I think otherwise that would have definitely given me enough penalty, or a small enough penalty to win, but I also could have won if I just didn't get silly WAs on, or a silly WA on G and a very silly TLE on F. So, I guess I just need to get good. But yeah, fun round. enjoyed the problems. I think the new authors did a very good job coming up with some pretty interesting tasks. This last one, problem G, I thought was a little less interesting. Felt like more of the sort of thing that you would expect to see on an educational round. Like it just felt like a pretty standard condensation graph problem, or really a number of or really like several different problems that all can be solved with a condensation graph, sort of layered on top of each other. But I feel like these sorts of like not especially interesting or sort of well-known problems are probably suitable for Div 3 contests, and it's nice that there's a place where newer competitors can practice solving relatively standard problems. I've also seen the idea in A before, but I mean it's hard to come up with original problems at that level. And everything else I enjoyed. I thought that B through F were all pretty nice problems. So yeah, thanks to the authors for the round, and thanks to all of you for watching. As always, if you have any questions, feel free to put them in the comments. If you're confused in general about a given problem, I would encourage you to read the editorial first, but I'm always happy to answer questions that are specifically about my solutions, and I'm also happy to, if you've read the editorial, I'm happy to talk through anything that's still a little confusing or that maybe isn't sufficiently explained in there. Yeah, so thanks for watching, and I will see you next time.